A double displacement reaction is carried out and the products formed are vanadium 2 phosphate and potassium nitrate. Determine both reactants and balance equation. First things first, then I'll give you the rest of the problem. So I'm giving you products. I'm telling you the type of reaction, and I'm giving you products. So why not write the products of the reaction? Vanadium is V2, means we have a 2+ charge on the vanadium. Phosphate is on the back. Polyatomic ion has a 3- charge. So the 3 parentheses PO4 2. That's a good example of a tough one from nomenclature to formula. Now, phase. Solid, liquid, gas, aqueous. Well, if it's a double displacement reaction, the products are going to have to be what? Has to be a solid, and one of them has to be aqueous, right? Well, if you look at your solubility rules, phosphates are insoluble except for ammonium and alkali metal cations. So this is solid. Potassium nitrate, KNO3. Aqueous. So, reactants, what do they have to be? I mean, this is not any different than the forward reaction, right? Going backwards, we have to swap the partners out. So what should our reactants be?
K3PO4.
K3PO4, okay. Potassium phosphate.
And V parentheses NO3.
Aqueous, because of our rules, alkali metal cations, potassium's alkali metal cation, it's soluble, and V NO3 2 because it's V2+, and this is also aqueous. Okay. Balance.
Get a 3 in front of those. Yeah.
Yeah. 3216. Balanced. Any questions? So now I would make this problem to where there's kind of like a not bullet, but like a part 1, 2. So now that we have figured out the reactants and now we know the products, now we know the phases, and now we're balanced, let's continue to work backwards. Again, stoichiometry can be worked backwards. I've always used that number. Let's go. 75.8 grams of vanadium 2 phosphate were precipitated. Determine moles of the NO3 2 reacted, assuming K3PO4 was in excess. All right, so now I'm making this one a little more hairy, if you will. Nothing that we don't already have the skills to answer. Is just reading comprehension and understanding what I'm asking and telling you. The information you're given, what I'm telling you, and then processing it that way. During this flood, I've been binge watching Luther. For those of you all who haven't seen it, it's a very, very good show, BBC show about a detective that deals with these crazy crimes, like these weird crimes. And that's what he does. He takes all the information in, and he processes it, and he tries to think a logical way forward. That's what you have to do in stoichiometry. So we have amount of product formed. Remember, we can always relate an amount of product to an amount of reactant and vice versa. That's what we've been doing. Up until this point, we've been going reactant to product. Doesn't mean that we can't go backwards, because law of conservation of mass said that our product had to come from this stuff. So we know a mass of product. We want to know how much of one particular reactant was reacted, meaning how much was used to get this much product, and we're going to assume that our other reactant, we have more than enough of it. So it was the one that was in excess that was left over, which means that our math is only really going to involve one value. We don't have to find the limiting reactant. I haven't asked you that. We don't have to compare reactant to reactant because I haven't asked you that. But I have asked you to find out how much was used originally. Up until this point, we've been giving you how much is going to be used, and we've been calculating it that way. So 75.8 grams of V3PO4 2, and we need to go to moles. Molar mass on this. We need 3 vanadiums, 2 phosphorus, and 8 oxygens. I tend to build this in the calculator as parentheses, 3 times vanadium, molar mass, in parentheses, plus parentheses, 2 times phosphorus, so on and so forth. Should be some fairly large-ish number. Hmm?
342.77 grams.
342.77 grams V3PO4 2. So now we have moles of product. We have a balanced chemical reaction, so we can go from product to reactants, reactants to products, all we want to, as long as we're dealing in similar currency, which is moles. So now we need a mole to mole ratio of 1 mole of V3PO4 2 and 3 moles of VNO3 2. I ask you determine moles, so we can stop here. We do not have to go to molar mass. Of that particular product. And this number is roughly 0.7. 0.7 moles of VNO3 2. So essentially, we've answered what we started with, right? This is giving us roughly how much of one of the products we started with. Any questions about this? Because the next question I'm about to ask is really going to determine how well you understand Stoic. That's as much as it's not like any of the problems I've given you so far, it's not much different if you understand it. Now look. Now here's question 2. This is a very good question. Using value from question 1, how many moles of K3PO4 were reacted?
Well, it's more than 0.7.
Huh?
So, well, it's more than 0.7.
Nope, wrong.
What's the excess?
It is the excess, but I asked you how much was reacted.
Yeah.
Right.
Yeah.
You can't get from number 1, based on this information, you can't tell me how much is left. I haven't given you any value to start with. You can't tell me how much more, you can't tell me how much excess is left, but you can tell me how much was reacted. And why? Why can you tell me how much was reacted? No. Why? If I just gave you that equation, you couldn't tell me, without any other information, you couldn't tell me how much was reacted. There's a couple different things. Number 1, I told you the limiting reactant. I told you how much of this fully reacted. I also told you that K3PO4 is in excess. You cannot make product in this reaction unless you have both of these. So to get this V3PO4 2, we had to react both of these. We just said that this much of one of our reactants has been reacted. This number relates
It's by 2, 3 to 2.
3 to 2. So 0.7 moles of VNO3 2 stoichiometry, dimensional analysis. If we want to know how much K3PO4 is reacted, what piece of information do we have? We have the mole-to-mole ratio as told to us by the balanced chemical equation. And it should be less. 1.4 divided by 3, about 4.7. What is it?
Yeah, 4.47.
0.47. Yeah, sorry, 0.47. I am by no means the human calculator. I keep mine very close. So it's less. Again, the conceptual understanding here is what's difficult for people. Once you see the math, you're like, okay, yeah, that makes sense mathematically. You cannot get product unless 3 moles of this reacts with 2 moles of this to create 1 mole of this. Since we know how many moles of this we did react, this ratio will tell us how much of this we used up. And that's essentially what I'm explaining. Not bad, I stayed in the camera view. Any questions about this one? That's a good one. And then we'll put up one more. I guess we'll call it difficult one. This is going to be posted. I'll post this just also for the students who couldn't make it. So this will be one of the lecture videos that you'll get access to. All right, let's see. We did synthesis, we did 2 double displacements. We haven't done a combustion. Let's mess around with combustion. Lactose. Lactose is combusted in oxygen. .9 times 10 to the 2 grams of lactose, and 8.3 times 10 to the 4 grams of O2 reacted. Determine products. Limiting reactant and mass of all products. So lactose, right? We know it's in dairy products. We have people that are lactose intolerant, right? Our bodies do not have the proper enzyme to handle this particular sugar. I think I'm slightly lactose intolerant. My mom has got it. She's got it bad. She can't do anything real milk. A lot of times it's actually onset by pregnancy, generally in women. They during pregnancy they lose that enzyme, or their body just stops producing. But you can eat a lactate, which is enzyme that you essentially digest to help with that in small amounts. All right, so we got a combustion reaction. We know lactose's formula, C12H22O11. This is a carbohydrate. This is no longer hydrocarbon. So most of our examples thus far, we were talking and using octane, hexane. We're using hydrocarbon. And we know a combustion reaction involves
CO2 and water.
CO2 and water. Now, lactose is a solid. I guess I should have to give that to y'all in that case. Most of your carbohydrates, we know that, right? Carbs, bread, generally is a solid. We associate that with. We know our products for all combustion reactions of hydrocarbons and carbohydrates are still CO2 and water. Gas, and again, your water can be either gas or liquid. In this case, I'm gonna do gas. Okay, now this is a little hairier than what we've been used to from a balancing perspective. Here's a balancing challenge because generally you don't have oxygen in all four places. Because you have oxygen in all four places here, you want to deal with oxygen last if you can. You want to deal with oxygen last if you can. My first approach
Get rid of the 12 carbon.
I actually would balance hydrogen first and see, and the reason I would do that is because look at this hydrogen and then look at this, and you see that once we balance this hydrogen with 11, we've actually taken care of all of these oxygens. But we still have 12 here. So this one might take some maneuvering. If you put the 11 here, then you get 22 and you get 13 oxygens. You got 13 oxygens here, but your carbon's not balanced. So I actually might balance carbon first and see what that does for me.
Double
Double,
lactose and then
double the
put the,
lactose in front.
yeah, and then put on the CO2. Put a what is it?
Well, if you double, you get
24.
24,
And 22.
and 22. Well, try that, and then the good thing about that approach, I like this approach. The good thing about that is if you do end up with an even number in front of O2, you can divide everything by the common denominator, and then get back to the easiest, the lowest one. So if you go 2, 24, 22, 48, and 22 is 70, right? But you have 22 here, so 70 minus 22 is the 48, right? So you need 24 here. Again, like I said, this isn't properly balanced because
You can
divide everything by 2. So that's what I was saying. That actually is not a bad approach if you realize that you're going to have to maybe divide at the end. But it ends up being what? 1, 12, 12, and 11, which is what I was going to do anyway, right? I think, well, I'm just thinking about it. It's just from, I couldn't explain it past the 11 that well, but it's just, I've seen so many of these that where I want to go first is just a form of habit. But yes, if you divided all of these by 2, then you end up with 1, 12, 12, and 11.
So it would have been wrong the other way because it's not the lowest.
Correct,
Yeah.
correct. But what I was telling him is I said, if you think something's going to make it easier for you mathematically, which that probably does make it easier mathematically using those even numbers, as long as you know to divide at the end, you're okay.
Yeah.
All right, so now we got it balanced, and we are given 2 masses of both. We want to determine products, limiting reactant, and mass of all products. So, first thing I would do is go ahead and do mass to mass. Again, since we need the mass of all products, might as well finish out the dimensional analysis all the way to mass for both of your reactants for a given product, and then you're cutting down your work at the end. So 2.9 times 10 to the 2 grams of C12H22O11, 1 mole C12H22O11, and this mass is going to be some, oh, I have it right here.
It's 342.34.
342.3, yeah. One mole, C12, H22O11, and we'll start with CO2 first, that's fine. 12 moles of CO2. 1 mole of CO2. 32 plus 12.01, 44.01. And there's your mass to mass conversion for one particular product, for one particular reactant. To determine limiting, we need to take the other reactant and compare it to that exact same product. And I said we have 8.3 times 10 to the 4 grams of oxygen. And 1 mole of O2 is equal to 32 grams of O2. We have 12 moles of O2 for every 12 moles of CO2. And we have 44.01 grams CO2 for 1 mole of CO2. Again, scientific notation on the values, don't change anything.
Mr. Brown, can we, like, does it not matter if we can either choose between CO2 or H2O as long as the ratios are correct?
Correct. It doesn't matter which one you choose from. In this particular case, in this particular question, because I'm asking for mass of all products, you're going to have to do a calculation using both anyway. But whichever one you want to use first or write down first to determine limiting reactant and determine the mass of the product, doesn't matter. It's just that this portion in both of these has to be the same. You can't use this reactant and use CO2 and then use this reactant and use water. You can't compare those. It's apples to oranges. But in this case, you got apples to apples. What are the values on these two?
447.4.
On the top one?
Yes.
447.
0.4.
Okay, and then on this bottom one, it's gonna be bigger. Should be, looks like it. Right, you would think it's gonna be bigger because of this number. What's that number?
$11,415.09.
Yeah. 11,000? Yeah, that's huge. All right, so clearly, we know that our lactose is the limiting reagent here, reactant.
You got 114 down.
Okay, this should be 12 over 12. 8.3 times 10 to the 4
It's 83
times 44 divided by 32, because you can leave the 12s out. This is the right number? It should,
Yeah, I got it.
yeah, it should be
That's
big
right.
number.
That's what I got.
Yeah, it should be.
1415, 10 to the 5.
Yeah, it's a big number. Oh, it should be bigger than that then.
114.
It should be 114,000. Okay. Either way, this is one of the few cases where it didn't make much of a difference because it's still limiting. You're going to get rid of this information anyway. Okay, so you have limiting reactant. You have the mass of one product. You must do one more dimensional analysis now that we know the limiting reactant is lactose to get H2O. So to get H2O, you're going to have to do this again. 2.9 times 10 to the 2, C12, H22, O11. 1 mole, C12, H22, O11. I'll try to fit it in here. 342.3 grams, C12, H22, O11. 1 mole, C12, H22, O11. For every 11 moles of water, and then 1 mole of water is 18.02 grams of water.
You've done water too many times. List it up. 15 plus 2. No, I'm just saying you've done it in your head too many times.
Oh, yeah. Water is, I mean, water's one that, even in the lab, you know, you're looking at water because you're looking at molarities, like when you're doing any kind of lab work, research work. Should be smaller than this number. So it should be about half of this number.
167.9.
A little under half. 167. All right, so there are your two product values. The problem set will be all over these kind of problems. I mean, mostly stoic, you know, your reaction types as well, predicting reaction, predicting products, writing phases. What in the problem set, I'll break those down into separate little parts, but I'll also have some problems where it incorporates all of them, which is what I've been doing here. I've been incorporating prediction, along with phase, along with balancing, along with limiting reactant, along with massive products. That's like the culmination of all of them. That's why I wanted to have this last class to be able to look at all of them. But you still need to be able to look at a list of reactions and be able to match it to a type. Single replacement, double replacement, be able to determine phases, just strictly predict products and not do any stoichiometry, and then also do the workout portion of it as well. Any questions about this one? This is a good problem though, because a lot of people may mess around and you know, they'll get frustrated on this balancing part. They'll be like, I can't figure out the right number. Practice your balancing. But I mean, it's just math. If you have a system where you're using a table and you're writing out values, by all means, just have the eraser handy. Again, I'll put this, I'll send an email, I'll go ahead and upload this here and put that in D2L so you can go back and look at it, because all these three are the style of problem that I would write in the workout portion of this test. That's going to be stoic based. And then I'll also talk, in the problem I'll put, how many digits these answers need to be so that you're not worried about the sig fig issues. You shouldn't be. And again, I'm going to be sending an email out to everyone about how we're going to handle the grading due to that, and just be looking for the problem set. That'll probably be posted tomorrow after I get done with the hybrid course. We don't have a lab today. Everybody be safe. That's why it's always valuable to learn how to swim. Teach your kids how to swim. Seriously, man. There's too many people that don't know how to swim. It's crazy. Just hold on to that. I'm going to grab those next week, lab stuff.